So the topic that we're tackling together today is the topic of graph transformations. This is in section 1.8. So if you had a chance to look at the preview activity that's there, I posted this introductory video beforehand. And I just kind of want to use the video real quick to point to kind of the main sort of organizing principle that we have in this section. So the main name of the game in this section is how does the shape of a graph, and by shape I mean kind of three things: the location of that graph within the XY coordinate system, the tallness, narrowness, or shortness and tallness of the graph itself, and then also its orientation, how it's reflected around the XY plane. How do those different operations on the shape of a graph get reflected in the formula of the function for which that graph is the graph, right? So the best way that I have to kind of explain, I think the best way to pick up how this all works is I just sent you a link in Slack right before class to this little applet that is just kind of like a little laboratory for playing around with this idea. And I don't know why it's not set up like this in the beginning, but if you set it up with 1, 0, 0, and 1 like this, then we're looking here at the beginning at the graph of the function f of x equals x squared. Right? It's this parabola. We tend to call this, and our textbook author tends to call this a parent function. It's one of those main shapes that you need to kind of be familiar with almost just at an automatic, right? F of x equals x squared, that graph, it has this parabolic shape, a parabola with its vertex at the origin. And so what the tools in this section are going to allow us to do are things like take the graph and shift it. So if I want to move this whole graph over by 6 units, for example, then I get this new parabola, this red parabola that's over here, which looks just like the shape of the parent graph f of x equals x squared. It's just been shifted to the right by 6 units. And the goal of this little interactive is that you can see how the formula for this graph is related to the formula for the parent graph. So for example, the parent graph here is f of x equals x squared. That's the one in the blue dotted line. And if we sort of strip out these extra looking ones here, we can convince ourselves that the shifted graph, the graph that's been shifted over to the right by 6 units, has the equation g of x equals x minus 6, the quantity squared, right? And so what's the relationship between these two things? The graph has been shifted over to the right by 6 units, and x in the equation has been replaced by x minus 6. So the main goal of what we're doing today is sort of build out your repertoire of if I want to shift a graph to the left, to the right, up or down in the xy coordinate system, if I want to stretch it horizontally or compress it horizontally in towards the y-axis, or stretch it upwards or compress it downwards, or reflect it horizontally across a vertical axis or vertically across a horizontal axis, how are any of those changes reflected in the formula for those functions? And as I said, this sort of table that I had here just a second ago is kind of the organizing principle that I favor for this, right? That we have 2 different kinds of shifts, stretches, and reflections that we can do. We can do horizontal shifts, or we can do vertical shifts. We can do horizontal stretches, or we can do vertical stretches. We can do horizontal reflections, we can do vertical reflections. And each of these sort of gives you the dictionary for what to do with the formulas for those functions in order to make that happen. So let's just do one quick example together before I turn you loose on today's activities. Let's suppose that I start out with, I don't know, how about the graph y equals the square root of x? And let's suppose that I want to find a formula for the graph that we get if I were to take this function and I were to do the following transformations to it. Let me make some space underneath here because we're going to need a little bit of space to write. Let's suppose that I want to do a combination of reflect it vertically, so reflect over the x-axis, so flip it upwards to downwards. And then let's say I want to stretch it out by a factor of 2 in the horizontal direction. So I want to pull it away from the y-axis, stretch it away from the y-axis by a factor of 2. And then let's say that I also want to shift it. Let's say I want to shift it down. And let's say I shift it down by 5 units. So let's say I want to do all 3 of these things to the graph of y equals the square root of x. So based on the information that's in this table, how would I begin? If the first thing I want to do is reflect this graph over the x-axis, what's my move? So if I want to reflect over the x-axis, that's what I call in this chart here a vertical reflection, right? The x-axis is my axis of symmetry, so I want to vertically flip this y equals square root of x. And so what I want to do is throw in a negative sign, replace something with its own opposite. And according to the chart, there are 2 ways of doing that. I can just throw the minus sign in front of the y in this equation, or equivalently, I can throw the minus sign in front of the entire expression on the right-hand side of this formula, y equals the square root of x, right? And that latter way, this way of doing it, is the more conventional. It's what most textbook authors sort of recommend doing, just so that your left-hand side of this equation can just remain y equals. So that's the tack that we'll take right here. We'll just throw in that minus sign in front of the radical and get y equals minus radical x. Okay? So that would be my first transformation step. To reflect over the x-axis, I'll throw that minus sign out in the front. Now, to take that and stretch it out by a factor of 2 horizontally, what should I do? The first thing to know about shifting and stretching is that they use different arithmetic, right? Shifting, moving a graph around, involves addition or subtraction. Stretching or compressing always involves multiplication or division instead. So keeping that arithmetic straight is an important bit to do here. So if we want to stretch, then we want to be multiplying something, right? And the something I want to multiply, here I agree with you, is I want to attack that x, right? Because that's my horizontal variable. So if I want a horizontal stretch, I should be multiplying x by something. So the question now is, what do I multiply x by in order to stretch out and make this graph twice as wide as it used to be? I should either multiply or divide by 2. Which one? If I want to make the, so let's try this. So let's go into the Geogebra Applet that I sent you, that I encourage you to play around with in the course of today's activities. So here's my y equals square root of x. The first thing we wanted to do is we wanted to reflect this thing over the vertical axis. And so you told me that I just wanted to put a -1 out in front of my f of x. So there we go. And sure enough, when I do that, my parent graph, which looked like this, is now reflected across the vertical axis, the horizontal axis, and now it looks like that. And now I want to stretch this thing out by a factor of 2. And so let's try putting inside of my f function, right, replacing my x with a 2 times x. And we'll see what happens. So if I do this, what does it look like happened just there? In case you missed it. Before I entered it in, it looked like this. And then it kind of went inward like that when I replaced x by 2x. So I wouldn't call that a stretch. I often would call that a compression. We're kind of making all these points closer to the vertical axis. So replacing x by 2x and getting this formula right here would appear to have shrunk, compressed my graph in towards the y-axis. When what we wanted is we wanted to do it the other way. Oh boy, I gotta bring my notes back up here real quick. There we go. Right, we wanted to stretch it out. We want to do the opposite of what it was that we just did. So if multiplying by 2 does the opposite of what I wanted to do, what should I do instead?
0.5.
Multiply by 0.5, or equivalently divide by 2, right? Whichever way you like. So yeah, we'll do that. We'll replace x by x divided by 2. Or if you like, 1/2 x, or 0.5x. So we get y equals minus the square root of, and yeah, I'll just write x divided by 2. So dividing by 2 directly to my x right here, that's what tells me I'm doing something horizontal. Right? And dividing by 2 accomplishes a stretching out by a factor of 2. So one of the things that sometimes people will say to themselves when they're doing these horizontal moves, right, where we're replacing x by something, is that everything kind of happens in bizarro world. It almost kind of happens backwards to your intuition. For example, if I subtract a positive number from x, instead of shifting it to the left, which is what we would usually think from a minus sign, it actually shifts it to the right. Multiplying x by something has the effect of compressing by that amount rather than stretching by that amount, which again is sort of counter to our intuition. So when you replace x by something, it tends to happen counter to what your intuition is. And what I usually tell people about that is that when I replace x by something, what I'm really doing is I'm really not changing the graph. What I'm changing is the graph paper underneath the graph. So if I multiply all of the x's in my graph paper by 0.5, I'm kind of compressing my graph paper squares inward, but then the graph, by contrast, is kind of doing the opposite of what the graph paper underneath it is doing. So replacing x by x over 2, now I've stretched out from the vertical axis compared to where we were before. And then the last thing that we wanted to do was shift this whole thing downwards by 5 units. So how would I shift this whole thing downwards by 5 units? So subtract 5 from the entire function that's on the right-hand side, right, is going to accomplish a shift downwards by 5 units. Let's check and make sure that that actually works the way that we expect. So in this little applet here, I'm just going to put a -5 in here for my k. And sure enough, you can sort of drag it. Yep. Now I've taken this whole graph and I moved it down. It used to start up here, originate at the origin and go down this way. Now it originates at the point 0, -5, and it goes that way. And sure enough, there's the equation of this fully transformed function at the end of the day. So this section is all about building that dictionary, that algebraic to geometric dictionary in your head. If you know what transformation steps you want to make to a graph, you can then figure out how the formula for that function has to change to accomplish those transformations, and vice versa. If somebody gives you a formula for a transformed graph, based on the parent graph, you should be able to figure out how to move it around and stretch it and reflect it to make it into the graph that you're looking for.